and I figured I needed to give a talk, even though I didn't have anything to talk about. And so the best thing I could come up with were just questions that I had, things I wanted to know that maybe the audience would solve for me. And it seemed to go okay. So when Jonathan had invited me to talk, the recent talks I've been giving have been on things like holomorphic dynamics, which is kind of fractally, but it's very hard to draw pictures of transcendental Julia sets. And so I don't have a good selection. And the most recent things I've been doing having to do with triangulations and the Veo-Peterson class also are not very fractally, they're kind of smooth. But the talk on random sets includes lots of fractals and lots of pictures. So it seems like the thing that was closest to the hearts of the audience. Let me share my screen and show you what I mean. So I will, for moment to moment, ask if anyone can hear me, because I have this like Zoom fear of talking into the ether and no one is actually getting anything. Can everyone see a title page that has three pictures on the bottom, with two of which sort of look like fractals on the left and the center?
Yeah, yes. That's good.
Okay, great. So what I want to do is tell you about each of these three pictures, and I have lots and lots of questions and very, very few answers. And so almost anything I say or anything you ask is an open problem or a conjecture of some sort. And roughly speaking, I'm going to spend about a third of my time on each of these pictures, not quite exactly, but roughly. And so if, for example, you get completely lost or bored at some point, you can wait to the next section, because these three sections are kind of independent. They all interact in some way under the surface, but not superficially. So the first picture, this one, this is something we call diffusion limited aggregation. And so let me show you how this is generated. Okay, so we start with a disk in the plane. We're just a unit disk at the origin, say. And what we're going to do is we're going to take a second disk. Think of it out here. It starts near infinity, and we're going to move it around at random. You can think of the center as moving like a Brownian motion. And eventually, the Brownian motion is going to hit that disk. And when it does, we add in a second disk. And so it just sticks to it. And then we throw in a third disk. And it moves at random. Let me sort of draw a random thing until eventually it hits one of the things I've already touched. And so we get a third disk, and a fourth, and a fifth, and a sixth, and a seventh, and we just keep going and going. And at some point, I'll just jump up to I think this is 100 disks, and then up to 1,000 disks, and then up to 10,000 disks. And now we have something that starts to look like a legitimate fractal. And so this is a DLA cluster, diffusion limited aggregation. And the question is, compute its dimension. While you're computing the dimension, you should also fill in other details like what is it exactly? Because this is just a large union of disks. What we'd like to think is that if I take this large union of disks and rescale it to diameter 1, I get a compact set of diameter 1. And then as n goes to infinity, this approaches some kind of fractally limit picture, which we see on the computer screen. However, there's no theorem that says that there is a nice, so you could imagine a probability measure on the space of compact subsets of the unit disk, and that the probability distributions on these DLAs would be converging in the limit to a probability distribution on compact sets. But there's no theorem that says that actually happens. So that's one of the things. One of the reasons is because we don't know how to rescale. If this is supposed to be, some radius, and we want to rescale it back to being radius 1, we should know how big R is so we know what to divide by. We don't know how big R is because we don't know how big the clusters are. Here's another picture of the same cluster where I've colored things according to when the disks were added. So you can see that disks that were added early in the middle, they're dark blue, and the things that were added later on, the most recent additions, are red on the tips. And again, this is sort of what you would expect when you see the growth model, that the most recent things are on the outside. Again, there are lots of interesting questions here which you don't know how to answer to. If I choose some radius here, maybe it's radius 1,000, when's the last time a disk enters it? So at some point, all the new disks sort of enter on the edge and they can't penetrate in very far, but we don't know how long that takes before they can't do that penetration. So that's, again, we could come up with some conjectures or ideas based on computer simulations, but we don't know that. Here's a slightly bigger one. I think we're at 100,000 now. And again, here's the colored version. So the main question is, how fast does the diameter grow? Or to another idea is just you take the center point and ask what the radius of the circle containing it is. How big is that? Well, we can put it on a computer and see, and if you do this a few thousand times and compute it and take the log plot of the radius versus how many disks you've thrown in, it's pretty straight. And the slope is about 0.5743. And so you can turn that into an estimate of what the dimension ought to be. I won't do that arithmetic for you, but I'm more interested in the growth rate. But that growth rate would turn into a dimension of what this set was. The set's actually connected, so it's bigger than 1. So it's somewhere between 1 and 2. And we'd like to figure out what that dimension is exactly. This is one of these problems which, when you ask a statistical physicist, they know the answer, and it's been known for a long time, and there's no doubt about it. But you ask a mathematician, they say, we have no idea.
Sorry, Chris, I thought the set was made of disks, and so it must be dimension 2.
Well, I'm talking about the tentative limit. So when we take the limit under rescaling, what we're getting is some kind of dendrite. So I'm going to go back. You're quite right, though. I mean, I'm being a little sloppy in my language here. I think of this more as a tea time conversation than a real seminar. So the idea is, you're right, this thing is made up of little disks connected to each other. But what we conjecture is that this is going to converge after rescaling to a compact subset of the plane, say of the unit disk. And that compact subset is going to almost surely have some fractal dimension between 1 and 2. And that's what we'd like to compute. And if everything works out nicely, we should be able to compute that dimension from knowing how fast the radius scales. But I wasn't going to do too much of those calculations. I just want to show you this plot that shows that if you compute this radius as a function, then you plot it on a log scale, it looks pretty linear. So it looks like the radius should be something like the number of disks to the 0.5743, or something close to that. Okay. Now, what do we prove? What can we prove? What can we prove mathematically? One is that it can't grow any faster than linear. I mean, the biggest that this cluster could be is if all the disks were in a straight line, and then the diameter is n. Because it's connected, it can't be any bigger than that. That's one bound. You can't be any bigger than that. The other lower bound is it has to grow at least like the square root, because if you take a disk of radius r, you can't fit in more than r squared unit size disks because the areas add up. And so the number of disks, the growth rate is at least square root of n, because if it was any smaller, there wouldn't be space. And that is approximately the entire theory of DLA, those two estimates. We can improve the linear growth one. So the one that says, well, at worst, they could all line up and the growth could be at n. We can actually do a little bit better than that. So back when I was in graduate school, I'd actually thought about this problem and came up with an estimate like this. But Harry Keston beat me to the punch, and he published a paper in which he proved that the radius, it looks like 2/3. And I'll just sketch the proof of this. This talk doesn't have many proofs or many sketches in it, but this is one where in just 1 or 2 slides, I can sort of give the reason why this is true. What we think of is, suppose the cluster has already reached some radius m. And then we want to say, well, if I want to go out to 2m, how long does it take me for the cluster to grow that big? Now, to go from m to 2m, I better add on about m more disks to reach across this annulus. How long does it take me to add on m disks? Well, as the disks come in, they add on at different places. But what I need to create a chain of connected things. So what I need to create a chain where each thing hits the previous one. So what I need to know is, what's the chance of a disk hitting like this one, not anywhere on the cluster, but that particular disk on the cluster. And that's something for which an old complex analysis estimate comes in handy. It's an old theorem of Berling. He said, suppose that you have some compact set in the plane, and let's say that this is radius r, so the size of this thing is r, and I take a unit disk. something of size 1. And then I send in a Brownian particle. This Brownian particle is eventually going to hit the set. And the chance that it hits a certain piece of the boundary is called the harmonic measure of that piece of the boundary. So what's the chance it hits this thing as opposed to anywhere else? And what Berling proved using ideas of conformal mappings and extremal length is that if the whole set boundary has radius r, diameter r, and you're looking at a set of radius 1, the chance of hitting it is about 1 over square root of r. And this is sharp when you have a line segment. If you have your compact set is a line segment and you're sending things in, and you just take at the endpoints the things of radius 1 over r, then the chance of hitting that is actually comparable to 1 over root r. So that's the best you can do. If the thing is not a straight line segment, it sort of has other arms, then the chance is going to go down of hitting it, okay? And using just this estimate with about the square root, you can sort of see that Keston's argument is correct, because you have this cluster of radius m, and we're trying to get out to 2m, and we have this disk. The chance of hitting this particular disk is about 1 over the square root of m. So what that means is I'm going to throw in about square root of m disks and attach at other places. But after about root m tries, with high probability, I should attach to there. And now I'm going to send in another root m disks, and they're going to attach places. But then eventually, after about root m tries, I should attach to that disk. And so it takes about square root of m attempts to attach the next disk, and I have to do that m times. So it's going to take me about m times root m attempts to grow this path all the way out to the annulus. And m times root m is m to the 3/2. That's how long I expect it to take to go from one size to double the size. And this is roughly the estimate of Keston that gives the growth rate of DLA. Now, the sketch I just showed you actually has a mistake in it. It's not too terrible of a mistake, but there's a sort of a technical mistake in it. I did prepare some slides to fix the mistake at the very end. If you want to ask me afterwards, I'll show you how you give the real proof of this. But this gives the right idea. You do apply Berling's theorem. This estimate of the square root is the right estimate to use. You just have to use it in a slightly different way than I did. So this is currently the best we know about the upper growth of DLA. It shouldn't be, because that estimate of Berling is only sharp for a line segment. When you have a line segment, then these endpoints get hit with about that root r probability. But if the thing has some different shape, you're going to get a strictly better estimate. And DLA does not look like a line segment. Here's a picture of it. Doesn't look like a line segment to me. If DLA looked like something like this, is sort of a, something that looked like this, then maybe you would get the square root. But in general, it has lots of these arms going off to infinity. So this Berling estimate should be better. And if you have a better estimate, that means you have to wait longer to attach these disks. You have to wait longer. It takes longer to grow. If it takes longer to grow, you get a slower growth rate. But no one has been able to figure this out. Now, I should have given you the warning label earlier on. There's a Stas Smirnov in Geneva. He has made the comment that graduate students and postdocs should not be told about this problem, because it's such a beautiful problem that it steals your soul, and it's so impossible that no one can do it. And so he's fearful that people in young and impressionable ages in their careers will just start working on this to no effect and waste their lives and end up working in a restaurant somewhere. And so I should warn you not to think about this unless you're willing to take the risk. Okay. Now, what about the other direction? The one that says, well, you can't pack more than, n squared disks into a radius disk n. Can that be improved? And the answer is probably, but no one knows how. So the estimate I gave you, that DLA grows at least like square root of n, is the best estimate that's known by anyone. So we don't even know that the diameter grows faster than root n, as in the ratio goes to infinity. What we expect, of course, is that the diameter grows like a power. It grows like some magical dimension, about 0.57. But we can't even prove this. We can't even prove that the ratio goes to infinity. So some people have offered prizes even just to prove the ratio is bigger than like 1,000. That would be a major breakthrough. We just don't have any idea. What's the problem? I mean, what's the problem with this? The problem is that if you suppose a DLA at some point did look very disk-like, then when you throw in a new disk, it can basically be added anywhere on the boundary with equal probability. And what that means is that this argument of asking, well, how long before I make a second hit and a third hit and a fourth hit, the estimate is now about 1 over the length, 1 over the radius. So if this is radius root n, so this is the radius, it turns out that what you get, it just gives you the trivial estimate. You don't get any kind of improvement. So what you need to show is that the thing is not a disk, that there's some quantifiable sense in at least it's sort of not a disk in some quantified sense. And no one has been able to figure out what the correct sense is. One thing I think might be useful is to consider the convex hull of the DLA cluster. And you can see in this picture, there are some areas of it that sort of have corners. And when you have corners, a Brownian motion is more likely to come in and hit near a corner. So we can prove that. So there are very concrete estimates that say if you are, if you have like any angle here, theta, and theta is less than 180. So if you can prove that there's a strict angle in the convex hull, then you can prove the chance of attaching to that disk is higher than you might expect. And then you can add on these chains and they will grow faster than root n. So if we knew that the convex hull of DLA was always had an angle in it, which was not a 180 angle, it was always, like at most 170, then we could prove a faster growth rate. So the idea is, how do you prove that it's not how do we prove that this picture is accurate and it's not, the convex hull isn't really a disk? It doesn't look like that. So this is what we'd like to quantify. One way of doing that would be if you were a disk, there would have to be lots and lots of vertices on the convex hull. If there's only a couple of vertices, then the convex hull looks like a small degree polygon, and it has to have corners in it. So it seems natural to investigate how many convex hull vertices there are for the DLA. And so I have a computer image for that too. So when you graph it, here is the number of vertices, and here is the number of convex hull vertices. It's sort of growing like this black curve on average. I don't know if you recognize that function, but to me, it looks like a logarithm. And when you do a log-log plot, the number of convex hull vertices grows more or less linearly. It looks to grow like 2.2 times log n. So again, that's only a speculation. Don't know how to prove that. That would be extremely interesting, though, if you could prove some kind of bound on the number of convex hull vertices of the DLA cluster. I can't guarantee that it would give us a growth rate. It depends on what this is, but it might. If you're clever enough to figure out how many convex hull vertices there are, probably you're clever enough to make some other progress on this problem as well. Just to show you a picture, here I've colored the disks in red or black according to whether, when they were added on, were they a convex hull vertex. So if we take the convex hull of this thing, it looks something like this now. And when we add in a new disk, it could either get added to an interior point, or it could get added and become a vertex of the convex hull. And the red ones were the ones that were added when they were convex hull vertices, when they were sort of on the extreme points of the convex hull. And you can see it's mostly red. So those convex hull vertices do gather a lot of the new disks. We expect that percentage tends to 0. So prove that. Don't know how to prove that. That would be reasonable. Here, this is just one of my last slides on DLA. For getting the lower growth rate, to show that it's growing faster than root n, we have to show that if it were ever a disk, that after some time it forgets that it's a disk and it starts to become non-disk-like. So we want to prove that DLA, if it should ever by chance become a disk, it would have to evolve into a non-disk. And what you can see is I've started the DLA on a big circle, pretending that the earlier cluster looked like a disk. And as these arms grow out, they don't look like disks anymore. It looks like little DLA clusters. And if we let it grow further, well, the part that's out here, that looks just like a regular DLA cluster. It's hard to tell from here whether I started from a single point or I started from a circle. So the DLA cluster does seem to forget what the initial shape was. So even if it was a disk at some point, it should forget that it's a disk later on. And because of all the empty space that's being left over here, we should be able to prove that we're not packing disks in as tightly as they can be packed. And so this diameter of this thing should be growing faster than root n. So, but this is the challenge. I've been thinking about this for 40 years. I mean, Stas is smarter than I am, but he's only been thinking about it for 20 years. But I don't know, this is one of my favorite problems. If you can solve it, please let me know. We would be very interested to know that. So that's the first mini lecture. I was going to go on and talk about something else now, but did anyone have a question? You've been very quiet. I should do a check-in just to make sure you're hearing me. Is everyone okay?
Yeah, fine.
No questions about the DLA? Do you want me to go back?
So I have a question. So, I mean, to me, like one of the big problems of DLA, it doesn't seem to be that it's a conformally invariant, even though it's sort of defined in terms of harmonic measure, right?
Right.
Is there any, I don't know, hope or chance that there is some sort of, let's say, asymptotically conformally invariant? So if you, let's say, I mean, you know, if you have already grown it for a very long time, so that, I don't know, let's say it's quasi-conformal with a low distortion or something, is there any hope, you know, some sort of weakening of the conformality?
Yes, I think there's a hope. I just don't know how to formulate it. I guess I don't want to spend too much time on that because I don't know what to say, and I'd just be filling the airways with sort of nonsense. But we certainly expect DLA to have some kind of conformal invariance. It's just not sure. I mean, it's defined in terms of Brownian motion, which is a conformally invariant object.
Yeah.
But I don't know how to answer your question.
Yeah.
I'm sorry.
Okay. Yeah.
So let me tell you about two problems about Brownian motion, which I like very much. The DLA section was the longest section, so that did take a little bit longer, as I predicted. So just to remind you, informally, Brownian motion is going to be a limit of random walks on a square grid. So here I'm thinking of starting my random walk here, and it moves around, and over time it traces out this path. Here I've shown 200 steps, and here I've shown 1,000 steps, and here I've shown 100,000 steps, and now it's starting to look like a real continuous random path. So in case you, this is the fractal seminar, so we probably had talks about Brownian motion, but I'll just remind you that in the limit, it converges to a probability measure on continuous paths. If you run it forever, you're going to get a dense set in the plane, but I'm only going to run my Brownian motion like from time 0 to 1. And so when you run Brownian motion for a compact time period, you just get a compact set in the plane. However, it's a two-dimensional set. We know it's two-dimensional, and we know it has 0 area. We also know it has infinitely many complementary components. So, I mean, here's looks like one of the bounded complementary components, and here's another one over here, and that looks like one over here, and there's one. And so there's infinitely many of these components, okay? Now, I want to talk about those components more a little bit later on, but the problem I'm interested in now are about paths that are inside the Brownian path. Like if I start here, and I start over here, the Brownian path is a continuous path, so it goes through this point, and you follow it around. Eventually, it'll get to the other point because they're both points on the same path. But if you follow the Brownian path, that's probably not the most efficient way to go. Maybe you could just connect the points straight. Well, then that path doesn't stay inside the trace. But maybe there's a different path that stays inside the trace, but is more efficient than following the path itself, which wanders everywhere. So the fact that the straight line is not there, there's actually a theorem of Robin P. Mantle. So he proved that Brownian motion never covers a line segment. So you can't expect that to happen. But does it cover a rectifiable curve? Can you take 2 points in here, which are different, and connect them by a finite length curve, which stays inside the Brownian trace? We don't know that. That's open. We don't even know how small you can make the dimension. If you can't get rectifiable, could you get like dimension 1.1, for example? We don't know that. We do know some examples of curves. For example, if you just take the outer edge of a component, if you just follow the say the boundary of the unbounded component, it turns out that's a Jordan curve. And the SLE technology, Greg Lawler and Werner and other people, they proved that that curve has dimension 4/3. So we know there are curves of dimension 4/3 in here. And then there's a more recent result of Zhang that you can actually get down to 5/4, which is a little bit smaller than 4/3. But can you get down to 1? That's the question. Can you get down to rectifiable, or can you get down to 1? Well, we could test this on a computer. I mean, if I have a random walk, I could say, well, if I want to reach a point over here, I mean, what's the best way of doing that within the discrete trace? Well, that looks like a pretty good path. This actually has the same length because it's sort of the Manhattan metric. On the other hand, if I did something like this, and I went over here, that would be a waste. I'm going too long. The computer can find the shortest path. So that's something the computer is good at, is finding a minimal spanning tree. And so if you just take the set of edges and compute a minimal spanning tree for that set of edges, the computer will do that in a microsecond. And then you can ask it, well, what is the shortest path between 2 points, like this point and this point? And the computer will tell you how far it is. And so the cluster is about, if you take n steps, the cluster is about root n across. And so I just asked the computer to, given the starting point, to go out to distance root n and see what was the shortest path that would take it from the starting point out to radius n. And we could do some experiments. Here, for example, there's a grid and a spanning tree, and here's a path that goes out. It looks pretty good. It just makes a few steps. Nothing too fractally going on there. Here's another example, a 10,000 step random walk. And again, we can find the minimal spanning tree, and we can find the path between 2 points. In this case, it goes like this. Let me actually just highlight it. It goes like this. And now this path is starting to look like it sort of oscillates more. And so the question is, does this converge to a fractal as n goes to infinity? So if you take a random walk on n steps, you get a cluster about size n. It's tending to Brownian motion in the limit if we rescale. Are there paths that connect distinct points whose dimension tends to 1, or maybe even tends to a rectifiable curve? So we don't know the answer to this. When you do this experiment of doing a cluster of size n and then trying to connect the origin out to radius n, this is the plot of how that distance grows. And it's kind of ambiguous, because the answer up here is that the tentative dimension is 1.0445 when I did 1,000 experiments like this. Well, 1.04 is a lot like 1. And it's also a lot like bigger than 1. I mean, 1.1 or 1.2 would have been a lot more convincing that it wasn't 1. You know, on only 1,000 trials, 0.04 is not very convincing, whether this is 1 or bigger than 1. So even numerically, I think we have to do a lot more experiments and a lot bigger examples. So these examples are maybe 100,000 or maybe 1 million. Go up. Well, here it says what so it goes up to, I guess, I forget the base. This is probably base E. So it probably goes up to around e to the 7, a few million or a few tens of million, perhaps. So even numerically, it's not quite clear what the answer is. But this is sort of the idea, is that you have a Brownian trace and you're connecting 2 points that are far apart. Can you do that with a one-dimensional subcurve, or do you need higher dimension? And I think this is a pretty interesting. This is called the percolation dimension, by the way. That was on a slide earlier. I didn't say it, but the percolation dimension is the lowest dimension of a Jordan curve inside the set. We don't know the percolation dimension of Brownian motion. In areas where the Brownian motion is kind of dense looking, these shortest curves sort of look kind of straight. It sort of comes down here without too much deviations. Places where the Brownian motion is sparser, then to stay inside the trace, the path has to wiggle back and forth. And here it wiggles. And so when we're asking if these optimal paths are fractal or not, it's sort of asking which of the 2 pictures is more common. When you look at a Brownian motion, is this picture more common, or is the other picture more common? And the answer is, in some sense, this picture is more common, because we know Brownian motion is 2-dimensional. And if Brownian motion is 2-dimensional, what does that mean? Well, if we give ourselves a grid here, and we have a 2-dimensional set in here, it's got to hit most of those boxes. If we knew that it always left out that box and that box and this box, the set would be porous. And a porous set has dimension strictly less than 2. But Brownian motion is 2-dimensional, so it's not porous. So we know that there are plenty of squares where actually the Brownian motion has to be epsilon dense. It has to hit, if we cutting the square up into 1 over epsilon by 1 over epsilon squares, it has to hit all of them. And in such a path, we have a pretty good chance of drawing a curve for the trace that looks pretty straight. It's only when there are omitted squares we have to go around them that the embedded curve might wiggle. So the question is, we have these squares. We sort of have this grid of squares. And some of these squares, the Brownian motion is very dense in. It looks very 2-dimensional. It sort of fills up those squares. Now, what P. Mantle showed was that the Brownian motion doesn't cover a line segment. So these squares cannot line up in a straight line in the limit. But can they percolate? Can these dense squares sort of form a connected path in the limit? That's the question. So we don't know. So there is another homework exercise for you to work on. One more Brownian question that's sort of related to the last one. The last one has been considered by several people. I don't know if this next one is so well known. So this may be a more novel question. So it has to do with these complementary components. We were talking about Brownian motion. It wanders around. When it wanders around, it forms these complementary components in the plane. And these complementary components can touch each other sometimes. For example, this component touches that component, and that component touches that one, and that one touches that one, touches this one, that one touches that one. I can sort of draw a graph in the plane where the vertices are the components, and I put an edge in if they touch each other. And in this case, all the components touch all the other components. Oops, I did something wrong here. Okay, is that true in the limit? And so this is a question of Wendell and Werner. He asked, suppose that you take the connected components of the actual Brownian motion, and you say 2 of them are adjacent as vertices of graph if they're closures, if their boundaries touch each other. Is it a connected graph? Can you go from any component to any other component by jumping just on the boundaries touching? So it really is enough to check if everything can be connected to the unbounded component. So there's the complementary component containing infinity, and if it's connected, then everything can be connected out to that one. If there's a component that cannot be connected to infinity, that means that the Brownian motion here has a complementary component. But whenever you try to take the components that touch it, and the ones that touch those, and the ones that touch those, and grow it out, there's a barrier. There's a curve in the Brownian motion, and these things can't get past it. Because when you start with the unbounded component and the things that touch it, they form a different component. But these connected components of the graph don't touch each other. So there must be a barrier curve, which has the property that this curve is not touched basically by the boundaries of any of these components. They can cluster on either side of it, but they can't touch it. And we don't know if this happens or not. So we can do, again, some experiments. Here, for example, is a finite grid. And here are all the different bounded components in different colors. But I'm more interested in coloring them by how far in they are. And so the next picture does that. So the outside is white, of course. And then everything that touches the outside component is colored light blue. And then the things which don't touch the outside but touch light blue things are colored dark blue. And there's only 2 layers here. There's only the first layer and the second layer. But if we go to a bigger example, like this one, we get 3 layers. We have the outside, we have the things adjacent to the outside, the things adjacent to those, and then we get components which are 3 steps in. And now we can do bigger and bigger examples, and you get pictures that look like this. And so here, maybe we could count the colors. There's 1, 2, 3, 4, 5, 6, 7. Look to me like there's 8. Actually, there's 10. It's actually written up here. The depth is 10. You can go in 10 steps from the outside. Okay. How does that grow as a function of n? I don't know. So I've looked at a bunch of these examples, trying to figure out some kind of formula or some kind of way of doing it. Here's a pretty interesting example. If you see, well, that's here in the center, there's a light green component which is pretty big. It's about this big, which is maybe about 10 or 15% of the whole thing, and it's fairly far in. It's about 12 steps in from the outside. So that is a pretty big component, which is hard to connect to the outside. So what we're looking in this picture is a macroscopic component, something of a given size, which takes infinitely many steps to reach the outside and the limit. So we're looking for components in the discrete thing, which are pretty big, but they take a huge number of steps through other components to reach the unbounded component. Can that happen? Well, the best example is this one that I currently have. So this occurs on a 50,000 step random walk. There's this component, which is light blue. You can see it, I'll try to highlight it, it's right here. It's 10% of the total diameter. So it's fairly big, and it's 12 steps in out of 20 steps. So the total depth is 20, and this big component is 12 steps in. So this is one of the best examples I've created in my experience of a large component that's fairly far away, but it's only 12. 12 is quite a long ways from infinity, which is what we're trying to get. We're trying to get infinitely far away, but that's sort of the record. My MATLAB code for drawing this sort of breaks down at some point. Once the matrices get to be, towards a gigabyte in size, then it tends to slow down and crash. So it sort of puts a limit. I haven't done any serious computing on like some serious computer to do this. This is just all stuff which done pretty quickly. But this is what we want to do. This is a graph of the component diameters versus how far they are from the outer component. And what we want to prove is that it tends to zero. So we want to show that if you are 30 steps in, or 40 steps in, or 50 steps in, then with higher and higher probability, your diameter is like 10% of the diameter of the whole cluster. It's 1%, it's 1.1%. That you want to prove that you just want a statement that says that if you run a random walk for n steps, and you take a component which is like 1,000 steps in from the outside, with probability 1 minus epsilon, its diameter is at most epsilon. So you want something that says components which are deep inside have to have small diameter with high probability. And it's not quite clear what the right formulation of that is supposed to be, but it shouldn't be too hard. Proving it, I don't know. And then there's the issue of if you could prove the discrete version, if you could prove that the random walks had this property, does that pass to the limit? Does that prove Werner's conjecture for the Brownian motion? Philosophically, it should, but technically, I'm not sure. So there's also the question of reducing the continuous case to the discrete case, which I'm not sure how to do. This is just a log-log plot of the same thing. We want to show these lines actually go down like they apparently do. This is the picture of the maximal graph distance to the outer component as a function of how big the cluster is. These are on the random walks. So again, it looks like it's following some kind of nice path, but there's not enough data points to really predict what this is. This asymptotic to a straight line, or is it maybe some kind of x log x curve? I'm not sure. You are welcome to do more experiments and tell me the answer. I would be fascinated to know this. So this might be something I'd have some undergraduates look at. If you take the log-log plot, it looks a little bit better. It does look linear. So my suspicion is that the maximum distance from the outer component should grow like n to the 0.36. I mean, at least in terms of fitting it. I mean, there's both a blue and a red line here. The blue is the data, and the red is the best linear fit. And as far as I can tell, they lie almost on top of each other. It's very hard to tell those things apart. And so I suspect there is a theorem that says what the maximum distance from the outer component should be, but I don't know how to prove that. So there's another assignment for someone looking for a nice problem. Okay. So the problem, as I said, is that if we start with a component and we take the things that are attached to it and we grow this out, is there some kind of barrier that prevents it getting all the way to the unbounded component? Okay. What would this barrier have to look like? This barrier would basically, when you take a neighborhood of this, there's only very small components. Basically, this curve would not be touching a large macroscopic component. The component sizes should get smaller and smaller as they approach this curve. And so this curve looks like it's made up of places where the Brownian motion is unusually dense. It looks very two-dimensional, doesn't look very porous along this curve because there can't be any large components which come close to this. So it looks exactly like the picture we were talking about before. Before we were saying if these curves, if these very dense boxes lined up and formed a curve, then we should have short, maybe rectifiable curves in the Brownian trace. And now we're saying, well, if these things join up to form curves, then Werner's conjecture should fail. So I'd like to propose that maybe we try to prove that either Werner's conjecture fails or there are rectifiable curves in the trace, but we won't know which one happens, just that one or the other of those things happens, but we won't be able to prove which one of them happens. So we can solve one of these problems without knowing which problem we're solving. I think that's potentially possible, that because both these things have to do with these very dense areas of the Brownian motion and whether they can, these boxes can be joined up to percolate, whether they can form long chains which are connected. Both these problems somehow come down to this question, but sort of in opposite ways. That was the end of my mini lecture on Brownian motion. I was going to go on and talk about one last topic, if you have the patience, but if you had a question about what I was just talking about, the Brownian motion paths or the components, I'd be happy to address that first. Anything there, or shall I go on?
So, I mean, these I don't know, these shorted curve paths that you consider, I mean, probably they're not SLE curves, right? I mean, that's sort of always the first question that you
Right.
ask. Yeah.
So I said that the known answers we had were, I think, 4/3 and 5/4. So the 4/3 were the boundaries of the components.
Yeah.
And that is an SLE curve. Is that SLE 6 or something? I forget. From the dimension you can tell.
I forgot that, but yeah.
So the boundaries of the Brownian motions are equivalent to SLE curves, and that's how they prove this number. So one of my proudest achievements in math was proving the boundaries of the Brownian components are bigger than 1 plus epsilon. I was very proud of that theorem with Yuval Perez and Robin P. Mantle and Peter Jones. We proved this back in the 90s. So Mandelbrot had conjectured the correct answer was 4/3, and after much work, we proved it was bigger than 1. And then a few years later, the SLE technology came along and actually proved something better, and our theorem went into the dust heap of history, basically. But still, that was a tough paper. I mean, we worked really hard to get that 1 plus epsilon, and so I'm still very proud of that result. The 5/4 is, I believe, another SLE path in the Brownian trace, something, I forget the name of it, it's like the harmonic explorer or the loop erased walk, or Jan, I believe, he proves that there is this other SLE path which you can prove is inside the Brownian trace, and its dimension is 5/4. So from 5/4 we can figure out which SLE it was. But I don't think I want to take the time to do that calculation because I only have about 5 or 10 minutes left, and I have about 10 minutes of material left. So maybe we could talk about this again in the questions afterwards. Okay. So the last thing I want to talk about is something of particular interest to me. And so I need help on this. I want to understand the picture that I'm showing to you right now. Let me explain how this picture is generated. Okay. So a triangulation is a bunch of triangles in the plane which meet edge to edge. Okay. So each edge of each triangle either meets the other triangles at a vertex or along a common edge. This would also make sense for what's called a dissection. In a dissection, you can have an edge of one triangle, which is not a full edge of another one, but basically I just want to consider triangles today. There's actually a problem about this I'm working on currently, writing up a preprint. It solves a problem in a famous book called Unsolved Problems in Geometry by some famous mathematicians like Kenneth Faulkner. So hopefully I can send you a preprint of this later in the year when I solve one of the problems in there. So, but it's sort of related to the story I'm telling you now, but indirectly, not directly enough to really bring it up here, except in passing. So triangle, hopefully you know what a triangle is. And there's the incircle, that's the tangent at the 3 points here. And then I'm going to draw something called the central section. So the central section is just meets where the incircle meets, and then these are the circles with the radius of the three things. So these are just circles centered at the 3 corners. And the neat thing is that each of these corners is foliated by concentric circles. And so I have a better computer-generated image of this. This is the basic picture. So triangle, you throw out a central region in the middle, and what's left has these nice circular arcs centered at the vertices. Now, when you start putting more triangles together, these will have their regions, and they will have their foliated curves. And then you can follow one to the next. And so as you do this, you can continue these lines. And I'll let the computer show you how to do this. So here's a triangulation, randomly chosen one. I chose 10 random points in the plane, and then I formed what's called a Delaunay triangulation of that. And then I'm going to form these central regions. And for each central region, what I'm then going to do is flow it along the curves I just showed you. And it looks like this. Now, the green points are the starting points. So there's certain places I begin, and then I follow these paths. Okay. And I know the number of starting points. It's 3 times the number of triangles. On each triangle, there are 3 of these starting points. So this cusp region has 3 vertices. And each of those vertices is a starting path. So I know how many points I start with. And the paths keep going until either they run into the boundary, or sometimes they can run into other points. For example, right here, you have this cusp region and this cusp region, and when you start them, the paths run right into each other. They intersect. So that's the other way. Otherwise, the paths keep going until one of those 2 things happens. And what I want to know is, how many of these points do we generate? How many times does this path cross a triangle boundary? Here, it doesn't look like too many times. Maybe it's 6 times n. But in more complicated examples, it can get worse. Here's a slightly bigger example. Oops. Well, I skipped a slide somehow. Let me go backwards. And here's the triangulation part. And you can see that it starts to, things can start to, if a path just goes straight to the boundary, that's pretty easy. But some of these paths can start to form these loops and keep going around. And so the number of points they're generating is getting larger and larger, which is sort of the bad thing. That's the enemy. I'd like to avoid that. Here's a blow up. This is starting to look like it might have some kind of fractal kind of a connection. Let's do some more examples. Here's a point with example with 60 triangles. And I form the central regions, and then I start propagating these curves. And when I start propagating these curves, the picture looks like this. And so what I'm interested in is basically the growth rate of how many of these intersection points are formed. And this is sort of a study of how much spiraling of this happens before you eventually go and hit the boundary. So you sort of go around and you spin, and then maybe you spin around here, and eventually you terminate. And how does this number grow? Well, we can put this on a computer and calculate this for a bunch of random examples. And here's n, and here it goes from around, this is 2.5, this goes up to 5, this goes from about 5 here, and this is 11. So the slope of this line is around 2.5. So, so each path here, there's n starting points. And on general, this thing crosses about n to the 1.5 triangles before it hits the boundary. And so in general, it's revisiting triangles because there's only n of them. So we expect there to be these loops happening at random. And the number 2.5 is very, very interesting to me. I will try by the end of the talk to tell you why. I might have to go over a minute or 2. I apologize for that, but I can't help myself. The fact that it's bigger than 2 is not surprising at all. A very special case of a triangulation is when you take a polygon and you just triangulate it by adding diagonals, okay? This has a very special structure because what happens here is that when you form the flow lines on a picture like this, you start on one triangle and you go into another one. Each time you go, you flow into a new triangle and you never come back. So this is the special thing. When you triangulate a simple polygon, the triangulation has no loops. So in a general triangulation, you can have several triangles all meeting at one vertex and a flow line can go around. But that doesn't happen for a triangulation of a polygon. And that means each flow line can at worst visit all the other triangles and then it has to stop because it can never repeat. And so the number of flow lines is at most n squared. And this actually happens. It's easy to create examples of this. Let me just jump ahead. When you have, say, n vertices here and n here and n here, so it basically looks like a rectangle, except the top part is slightly curved. Then when you start one of these paths here, it works its way down here, and I'll show you the computer image. They look like this. And so n triangles definitely gives rise to n squared dots. Each starting dot generates a path, which is n long. And so we definitely have to get this. And this is stable under perturbations. You can take this picture and move these vertices a little bit, doesn't change the estimate. So inside the space of triangulation, there's an open subset where we get n squared. So when we're computing the average, that subset contributes n squared. And so we can't hope to do better than that. So the 2.5 was bigger than 2. And so I'd like to explain where the 0.5 comes from, because I don't want it to be there. I'd really love this to be 2. That would be great. Unfortunately, the numerics indicate it's not. Here is here's the last example I'm going to show you. So everyone should see something that looks like an annulus built out of equilateral triangles, okay? It's a very special triangulation. All the triangles are nice 60, 60, 60 triangles, and they're all arranged in this nice loop. I'm not saying what I'm going to do in the center because the center turns out not to be very important. The critical thing here is that when you take one of these triangles and you draw the incircle and then you connect these up, so you're drawing these up, the secret is right here. This point is the same for both of them. And when I connect these up, it's the same. And when I connect these up, it's the same. So now whatever, if I have a path in here wandering around and it enters here, the flow line takes it here, then the flow line takes it here, the flow line takes it here, and it dumps it back in the center. Because of the way these things are set up here, whenever you hit the boundary of the inner parallelogram, the flow line always comes back. It can't leave. So in this special arrangement, no matter how I triangulate the inside, I can never leave. I can never hit the boundary. So, so whatever I do, it comes back in, I wander around, I come here, it goes around here, I wander over here, it goes around here, comes here. I can never get out. And if I actually triangulate the inside some way, and then I show you the flow lines for this, this is what it looks like. And so in this case, the number of contact points is infinity. And so there are triangulations where the answer to my question is not n to the 2.5, but it's an infinite number of things. And so this is like a pole. We're thinking of computing a number, which is a function of the space of triangulations. And we know that there are large blobs where it looks like n squared. We also know that there are particular points where it blows up. It has like a pole at that point. But are these poles rare enough? Are special configurations like this small enough that we still get a power law for the number of hits? That I don't know. So I'd like to figure this out. I can tell you why. If you, I guess my time is up, but may I please have maybe 1 or 2 more minutes just to finish my thoughts? Would that be okay?
Go for it, Chris.
Okay. So if you take that example before and you randomly jiggle it, then when you randomly jiggle it, this perfect symmetry doesn't hold, and now things can escape out. So now you have paths which do get out to the boundary. And so the idea is that one bad example where you get infinity is like an isolated point in the space of triangles, that if you perturb it randomly, go in any other direction, you get back down to a finite number. So the picture really should look like this somehow in polygon space, in triangulation space. Now, the reason why I was personally interested in these flows has a very concrete reason coming from numerical analysis. It has to do with triangulations. When you're solving a differential equation, a PDE on a region, usually what you like to do is to put a mesh on the region. And so very often you triangulate the region in some regular way. and then you approximate your continuous function by some discrete function defined on the vertices of your triangulation, and you approximate your differential equation by some kind of linear or maybe nonlinear equation on these vertices. So you basically reduce a continuous problem, hopefully, to some linear algebra problem for a function defined on the vertices. And the shape of the meshes turns out to be important. When you have triangles that have angles bigger than 90, some bad things happen. In fact, the closer to 180 you get, the worse things are. So you really want to avoid triangles which are long and narrow, which are like 179 angle. That would be kind of chancy. If you get everything under 90, that's called a non-obtuse triangulation. And so there's lots and lots of things in the literature. Just to give you an example of one thing, when you're solving a finite element method, you reduce to a linear algebra problem. And whether you can solve the linear algebra problem depends on the condition number of the matrix. So the condition number is the norm of the matrix combined with the norm of its inverse. And we like that to be small so that numerical methods work well. In general, when you triangulate a region and you're applying the finite element method, that condition number grows exponentially in the size of the triangulation. That's kind of bad. Steve Vivacis showed, though, that at least in certain problems, if you had these non-obtuse triangulations, the condition number grows linearly instead of exponentially. That's much better. And so there's a very strong motivation for triangulating regions with things that are kind of close to equilateral, like no worse than 90 degrees. And so the question was, if you were given a general triangulation, let me just give myself a little more space here. So if I were given some triangulation that maybe had some obtuse angles in it, could I improve it? Could I take this and could I further cut it up into smaller pieces in which all the smaller pieces were in fact non-obtuse? So is there an improvement? And I'd worked quite a while on this, and eventually I did show that you could do this non-obtuse refinement. I won't say anything about how this is, but the secret is that I showed that you could do it in polynomial time, which I accidentally unshared my screen. This is the next to last slide, so let's just try to get through it. And the polynomial bound I got was 2.5. Now I showed you a 2.5 before. Is that a coincidence? And I don't know, but I'd like to find out. So the way this non-obtuse triangulation thing works is the following. If you have a triangle which is obtuse, it has a big angle, one way of cutting it is just to add the altitude here. So you just drop this down, then this is 90 degrees by definition, and these other angles are small. That's fine, that works. But if there was another triangle over here, and you drop its thing down, these 2 points aren't matching up. So this is not a triangulation because you have a long edge of one triangle doesn't match with the short edge of the other one. So in order to fix this, you have to take this point and you have to push it forward, okay? And this point, you have to push it forward, and then you have to somehow triangulate these quadrilaterals you have. But the main thing is that this vertex, when you try to cut the triangle up, creates a new vertex, which then has to be propagated. And if you had another triangle over here, that problem would have to go. And if there's a triangle there, that would have to go. What you get are these flows. And what happens is that the crossings of the triangle flow I already described to you, these crossing points give you the vertices of the triangles for this theorem. And so to prove that you can get away with a polynomial number of triangles, you have to show that these flow lines only generate a polynomial number of points, okay? Now we get to cheat. In the application, if there's too many crossings, you can perturb the flow. You don't have to take exactly this circular flow. You're allowed to change it a little bit, and still the application will work. So you're allowed to make perturbations of it. And what I show is that you can always perturb the flow so that you create new closed loops. And instead of hitting the boundary, you can just wait. So if you have a flow that is coming around and is revisiting the same triangle a lot, eventually comes close to somewhere it's been already. And when it comes close, you can change it and have it join, and now it forms a new loop. And once the loop is formed, then no new vertices are formed. You're just going through the old vertices you already know about. This is very similar to something called Pugh's closing lemma. And my argument shows that in this triangle flow, even if we generate a huge number of points, when we do this closing method, we can always get down to n to the 2.5. But I was interested in studying what's the average case if you don't do this closing. If you just let the flow go by itself and you don't do this, because the closing is very technical and very difficult. It's very complicated how to close these loops up. So if we just threw that away, how good would we do on average? And I did these experiments on the flows, and I was getting this number 2.5 that says on average, we're doing exactly as well as the worst case in the complicated thing. And this is bizarre to me because I don't know any reason why this should be true, but if you can figure it out, I would be happy to hear it. Sorry to have gone over. That was very bad judgment on my part. I apologize, but I hope you don't mind too much. Thank you very much.
No problem at all, Chris. Thanks very much. So I guess, do we have any quick questions?
As I said, I'm happy to hang out for longer questions if I know you have to go. But,
I'll have to go because I have to go teach, but I can leave the meeting running, I suppose, if people want to hang out and chat. Anyway,
well, I'm willing to hang out. I don't know. I'll keep my eye on the participant list. Once it's down to one, I definitely will probably leave.
So, Kurt, you've unmuted yourself. Do you have a question?
No. Sorry.
Oh, sorry. Does anyone have a question?
Yeah, I have a question which may be stupid,
Sure.
but the middle part about lines or rectifiable curves inside Brownian motion
Yes.
remind me a little bit of the Erdős similarity problem in a way.
What problem? I'm afraid I didn't quite hear.
The Erdős similarity problem, which asks whether every set of positive Lebesgue measure contains a similar copy of every countable set, or
Yes,
some
okay.
variation of those quantifiers. Now, I was wondering what is known about a typical Brownian motion. If you take a typical Brownian motion, its dimension is 2, but its measure is 0.
Yes.
Will it contain a copy of every countable bounded set, say? A similar copy, or even
Right.
finite sets?
I don't know offhand. Probably so many people have studied Brownian motion. The answer is known or could be known. Let me think about it for 1 minute before I'll look like I'm thinking hard here. I put on my thinking face. I think that's probably false. So I guess my thinking on that, let me just open up a screen. I'll share my screen again. And so we start the Brownian motion at the origin. The idea is that since the Brownian motion has area 0, the chance that it hits a particular point is 0. So if I'm start at the origin, I say, what's the chance I hit 1? The probability of hitting 1 ever is 0. I don't hit it. Now, if I just have a 2-point set, I can rescale things. So I could multiply, I could dilate and rotate so that my favorite point became 1. Or, right. So I think I can hit any 2 points. So I can hit any 2-point configuration. If you give me a 3-point configuration, say I want to hit those 3, something similar to those 3 points, like an equilateral triangle. Well, I start at the origin. I take some point here to be my second point, and then I take the quadrilateral there, the triangle there, that'd be my third point. The chance that I hit that third point is 0. And I've already used up my scaling to make it hit the second point. I don't think there's anything I can do to make it hit the third point. So my intuition is that the Brownian motion, well, no, but I could choose other starting points, yeah. So does Brownian motion contain every similar triple?
So I'm
not sure. I'm confused.
I don't know if I should be stating my opinion right now, but
yeah, go ahead.
Like Brownian motion almost surely has Fourier dimension 2.
Mm-hmm.
And there are certain Fourier decay conditions that guarantee that you contain these types of linear configurations. There's a work by Chan, Laba, and Pramanik that
Yeah.
gives an explicit Fourier decay condition that guarantees that you contain a 3-point configuration, or a finite
Yeah, so
configuration.
I was starting to argue it couldn't contain it, but as I argued for it, I was convincing myself otherwise. So
I don't know if the Chan-Laba-Promanik paper applies to this situation,
Mhm.
but
it's a place to look, a place to start. So yeah, I
Yeah.
don't know if that had been done. I mean, I would, if I actually wanted to know this, I would probably get on my email and write to Yuval Perez or Chris Birdsey at Washington, or a few other people, Robin P. Mantle, and ask around if this was known. I mean, this is the sort of thing that there's so many papers on Brownian motion, this might be in one of them someplace. Or if it's not in one of them, it might be that it follows from some known theorem. So just not known to me personally. So this sounds like something doable. But I don't happen to know the answer, but it's certainly a natural question, yeah.
Thanks.
I was muted there. Thanks very much for the question. So I unfortunately, I'm going to have to go now. So I'm going to stop the
All right.
recording.